2.3 systems of 3 variables. There's only a few instances in this lesson where we can use substitution. But since it's got 3 variables, it's going to have 3 equations that we're going to have to solve. This is just a general strategy for solving systems of variables but it's with elimination. There's another method, but we don't go over that in 1010, although we used to. Seems like we used to in 980, but either way, first thing, you got to choose a variable to eliminate. You got 3 variables to choose from, x, y's, and z's. Choose one to eliminate. Then you choose one equation to use twice. That may sound weird. We're going to use one of the equations twice, whether you want to or not. Okay. So because there's 3 equations, you're going to combine that one equation that you've chosen to combine it with the other 2 equations. And remember, you have a variable that you're eliminating. So when you make a system which is going to have 2 equations, you're just eliminating whatever variable you have chosen. But be methodical with that. So don't just be like, I'm going to eliminate the x's, because sometimes it can make things quite difficult. 3, use the one equation on the other 2 and eliminate the chosen variable. I guess I just kind of explained that. Again, we want to, I'm saying combine, it's just that we're using that elimination on the 2 sets of equations to eliminate the variable that we've chosen. But this will create 2 new equations, but then we'll only have 2 variables, which allows us to solve those 2 equations like we would a regular system of equations. I know some of this may not make sense, but hopefully it will when we go over the work. 4, use the 2 new equations to solve for the 2 remaining variables, just like I said, just like you would. And usually you're still using elimination with those 2, but you could use substitution. And then 5, use the 2 variables to solve for the final variable in one of the equations. And then once you get that variable, you can go back to the 2 new equations and solve for the variable that you don't have from the 2. And then once you have those 2 variables, you can use one of the original equations to solve for the final variable. But of course, the last thing you should do is check all 3 equations, because we're just using a calculator for it. Check all 3 equations just to make sure that you get true statements for all 3, because if you don't, it's going to suck. Because this is going to be a lot of work, just right? Like what I just said sounded like a lot of work, and I do make mistakes on this. So if some of you guys are like, what the crap is going on? Yeah, I make mistakes too, so just be prepared. All right, this one, here we go. So right here, let's say that we were choosing a variable to eliminate. Again, be methodical about this. Take your time and think about it. Looking at this system, I do not have to solve for z. How do I know I don't have to solve for z? Because it gave me the z right here. No need to solve for there. Is this going to happen all the time? No, we hit the jackpot. You're going to see one like this, of course, right? So what I can do now is I see the second equation here has a z and a y. It doesn't have an x. So right here in this equation, I can solve for y. So I'm going to set this up. Let's take this equation. Let's move this over here. Right, so it's showing y minus 2 times, that'd be 2 times z equals 14. But now we have a z value to replace into it. Now again, usually there's a lot of work that goes into solving for this z, but right now, no problems, right? So in solving for this one, I'll do it in green, I guess. So negative 2 times negative 4 is positive 8. So that would be y plus 8 equals 14.
For a minute, I thought that was a negative y.
Oh yeah, the arrow, my bad. But thank goodness it's not. So yeah, it's 0. Y now equals a 6. Boom. You see how this, and this is, again, this is usually how this process would work after we have solved for one of the variables. So for the other problems, there's a lot of work in between getting to that point where they started us off, which is good. It's nice to start off in something that's fairly simple. Okay, now the first equation has the x's, y's, and the z's. So let's rewrite. I'm going to try that over. Let's rewrite that one. 4x minus 5y plus 2z equals negative 25, or at least it should be. So I know the y value. I made it green right there, so that's a 6. And then the z is negative 4. All right, let's solve this. So negative 5 times 6 is negative 30. 2 times negative 4 is negative 8. So now I've got 4x minus 30 minus 8 equals negative 25. Combine like terms. Negative 30 minus 8 would be negative 38. So now we got 4x minus 38 equals negative 25. And a couple principles of equality here. So add 38. But yeah, I gotta preserve some space there. Negative 25 plus 38 is positive 7. And I can drop my 4x. 4x.
I think it's 13. Yeah, it's 13.
It's not 7. It is 13. Thank you. So let's fix that. There we go. And I gave myself more space there, so that's also good. Divide both sides by 4. And I'm just going to show it as a fraction. X should be 13/4. Okay, now, again, is this actually going to work? Well, I just go to my calculator, and I do 4 times 13/4 minus 5 times the 6 plus 2 times negative 4. Enter, and that's negative 25. That one works. Let's try the next one. Y is 6 minus 2 times negative 4. Enter, 14. And then the last one, we don't really even have to check that one, but we did find the x, so I'm gonna box that in.
Can you recommend?
Okay, so this answer we're gonna need to write as an order triple, no problem. But first, okay, so let's set this up. Let's first figure out what variable we want to eliminate. Now, right here, I'm looking. The y's are going to be very easy to eliminate. Okay, so remember, start out with some purpose. Start out with thinking about what process you want to use. What variable looks like it's easier to eliminate here? Looks like it's the y's. And the reason that is because this y has a positive 6, and then these other two are negative 6. They're opposites. All right, so the first thing I'm going to do here is I'm choosing to eliminate the y's. Okay, so I'm choosing to eliminate the y's. And what I'll do then is we do have to use all 3 equations. So I'm going to take the first one here, 2x plus 6y minus 6z. And I will combine it with the second equation. I think that's lined up pretty good. But I'm also going to take it, let's put it over here, and I'm going to combine it with the third equation as well. Okay, so this is kind of a new system that I'm setting up to eliminate the y's, right? That's the first thing we did. Now we've set up these 2 systems, and we're going to solve both of them. And by solve, I mean we're going to eliminate the y's, okay? So I'm going to add the x's, y's, z's, and constants. And what happens here? Well, I got 2 x's plus 4 x's, which is 6 x's. The y's, they zero out as planned. 6y's minus 6y's is 0. Negative 6z plus 5z would be a negative 1z. And in fact, we can just show that as z, if you want to make that a phantom 1. And then that would equal 4 plus negative 25 is negative 21. So that right there, what I haven't read, that is an equation that I can use now in the system. But the equation it no longer has a y. So I'm now looking at creating a system that has 2 variables, and I'm going to finish the system with this second set of equations. Okay, so again, the y's, I don't have to do anything with these 2 equations to force the y's to have opposite coefficients. Be aware, though, if you chose to eliminate the x's at this point, you'd have to multiply this equation, the top one, by 4 in order to force those coefficients of x to be opposites. But for the y's, they're already opposites. We've chosen to eliminate the y's, and so that's what we're going to stick with. One last thing about that, though, is the z's, right? If you were to say, I'm going to eliminate the z's, you'd have to multiply the bottom equation here by 6, all of the terms by 6, in order to get these coefficients of z's to be opposite. So be aware that may happen on the assignment, but this one just happens to work out where the y's are going to eliminate. So let's add each of these together. 2x's plus negative 8x's would be negative 6x's. The y's, 6y minus 6y, zeroes out. Negative 6z plus, that's 1z, that'd be negative 5z's. and that would equal 4 plus 35 is 39. So these two equations that we have in red and purple, I can now use those two to create a system of equations. Now, let's see if we can make that better. So this is what I have, and yeah, that cleaned that up a little bit, but you'll notice here that we can look at the system 6x minus z equals negative 21 and negative 6x minus 5z equals 39. And we should think, well, if I looked at this and started with just this system, what would I eliminate? And hopefully you can see there that if I choose to eliminate the x's, they will eliminate right away. I don't have to actually multiply the equations by anything. So I'm going to stick with that and add the values together. So 6x plus negative 6x, that zeroes out as planned. That'd be negative 1z plus negative 5z's, that's negative 6z's. And this equals negative 21 plus 39, which is 18. So this is now an equation that I can solve for z. So that's what I will do by dividing both sides by negative 6. So this will tell me what z is. Z equals negative 3. So now that I have that z value, it's very similar to what we saw in that last problem, but we had to work to get to this point, and you can see what we did to get to that point. But I have a z value. I want to solve for only one value, and I can see I've got this red and purple equation. It's part of the system, and so I know if I replace the z's in either one with this z value, I can solve for x. Also, I see that, at least for me, I think the red one's going to be easier. So that's what I'm going to do. I'm going to take that z value and replace it with negative 3. So this equation then becomes 6x minus negative 3 equals negative 21. So let's solve it. I got minus and negative, so I show that as plus. And then I can use the principle of equality, just subtract 3 from both sides to eliminate that plus 3. So that I can drop my 6x equals, because that zeroes out, negative 24. And then we'll divide both sides by 6. That will give me just the x. X equals negative 24 divided by 6 is negative 4. So I now have an x value. I have a z value. All I'm missing is a y value. Now, I can't use the red or the purple equation to solve for y because there is no y's. We eliminated the y's as we had planned. So this means I've got to go back to one of the original equations. Doesn't matter which one you choose. I'm going to choose the top equation. Okay, so let's go back to the top equation. But now we know the value of x is negative 4. So let's replace that with negative 4. And then let's replace the z with the value we found, which is negative 3. So all I'm going to do is I'm going to solve this equation for y. So 2 times negative 4 is negative 8. Negative 6 times negative 3 is positive 18. Okay, so I still got the plus 6y equals the 4 as well. Combine my like terms, negative 8 and positive 18 is positive 10. So now 6y plus 10 equals 4. And we'll subtract 10 from both sides to zero that out. So now 6y, that zeroes out. 4 minus 10 is negative 6. Hey, that's going to work out real nice because now when I divide both sides by 6, I get the y value is negative 1. Okay, so I've got my x, y, and z. If they give me true statements for all 3 equations, then I can fill these in, right? So I got my x, which is negative 4. I got my y, which is negative 1. And I have my z value at negative 3. But will it make these true? As it turns out, and I already did this on the calculator, by replacing each of the x's with negative 4, each of the y's with negative 1, and each of the z's with negative 3, I get these answers. Okay, so that means that all 3 equations are true statements. I'm always a little nervous when I do this because if I make mistakes on these, you can see how long this process is, and you kind of have to work backwards to see where you made a mistake. Sometimes it's just typing it into the calculator, so be careful about that too. But when I checked all 3 of them, they gave me correct or true statements on all 3, and we can rest assured that we've done this correct. All right, so this system, again, let's see if there's any of the variables that we can eliminate pretty quickly. I'm looking at the y's again. Actually, the x's would be 2 because this coefficient is a negative 1, and I can easily make that be an opposite with the 5 right there, okay? So that's what I'm gonna do, and actually it just kind of makes it different than the last one as well. So on this one, I'm eliminating the x's, okay? And again, it's just really to be different from what we did last time. So I'm gonna take the top 2 equations, and then I'll work with those, and then I'll take the top equation. Again, I'm working with that top one specifically because it has the opposite, and it's a phantom 1 coefficient of x. So I can make it be an opposite to that 5x pretty quick. But I'm gonna need a little bit more space, so here we go. So let's start with this set on the left. Okay, so I'm gonna take this equation, I'm gonna multiply it by 2 so that the coefficients of x will be opposites, right? So that's gonna give me negative 2x plus 4y plus 8z, and that will equal negative 4. Okay, then we got the other equation. And now I'm ready to add these two together. Now the original intent here, right, because I'm going to add all of these together. The original intent was to eliminate the x's, and we've done that successfully. The problem is that I've eliminated the y's and also the z's, which means on the left side of this equal sign, I really just have 0. I have nothing on the left, just 0. But on the right, you can see that we would have negative 4 plus 5, which is 1. Okay, now this brings up a question. And it doesn't matter if you have a variable with the 0, by the way. But we have to ask ourselves a question because the equal sign is a conditional statement. Is it true or is it false? And we can ask ourselves, when is 0 equal to 1? And the answer is never. It's never equal to 1. Okay, so this means that, at least from this, that if you were to graph these, let's say that you were to graph these and you found them to be lines, they would be parallel. Yeah, so essentially we're saying that the graph would show a parallel relationship. Or in other words, the graph never meets. The lines never meet, if you will. And what this also means for us is that really there's just no solutions. Now, the good news for us at this point is that we don't actually have to solve the other one. That's just as far as we need to go. Now, that's just the relationship of the 2 equations that we had. It's possible you may find that maybe you could find a new equation by eliminating the x's here, and you could. But that doesn't matter. So these 2, you could say they do intersect, but these 2 right here that we started with, no. So that means, but we need all 3 of them to meet. And by the way, they're not lines, not that that matters, but all we need to understand is that we have 2 equations that have a parallel relationship. It doesn't really matter what happens after that. We know that all 3 of them have to meet, and one of them never will with another one. That's all that matters. So on this problem, we chose to eliminate the y's and x's. Let's choose to eliminate the z's on this one. So we're eliminating the z's on this one. Okay, so let's go ahead and let's take that top equation. And I just chose that arbitrarily, by the way, the z's. Some of you would say, I want to do that a little bit more methodically. Maybe you choose to eliminate the y's instead, and the x's would be a good option as well. Okay, so I got my top equation, and I can see that changing that z coefficient to opposite is not going to be very hard. Let's see. Let's take that top equation again, and then I'll just combine it with the bottom one. Now I could have chose to just combine these 2 if I wanted to, but it doesn't matter. And let's separate these just for the sake of space. All right, so let's start with these 2 equations, right? So I got to take this top equation. I need to multiply it by 2 so that my coefficients of z's will be opposites. All right, so what does that give me? It gives me 6x plus 2y minus 6z equals negative 64. And then the second equation, I think some of you notice what's going on here, and if you do, that's good. If you don't, that's okay too. Remember, we were choosing to eliminate the z's, and they do eliminate. That was part of the plan. But just like the last problem, we also notice that the x's and y's zero out as well. So I end up with 0 on the left, but notice I now have negative 64 plus 64, which is 0. So I'm going to put a question mark over that equal sign because we need to address what this is telling us here. And I'm going to put in the form of a when. When is 0 equal to 0? And the answer to that is it's always going to be equal to 0. What that means for us is that these two lines, they're exactly the same, okay? And they're not lines, they're planes, but that doesn't matter. We're essentially saying that these two equations are the same, so if you were to simplify this one, let's say you divide both this whole equation by -2, you'd get exactly the same equation. And so we end up with a situation where it's just always the same. So the two equations are the same, and that tells us we have infinite solutions. And yeah, I can spell infinite right, or at least the computer can. And that right there, that's as far as we need to go. Once we see that happen, we don't have to worry about this, creating a new system, solving a system of two equations, and then working backwards from there. That's it.